Okay, so we are recording now, and today is chapter 24.
The number of hours in a day,
The number of
approximately.
hours in a day. That is true. Let me just adjust my audio. Can you talk a little bit, Marinho?
A little bit, Marinho. Well, it didn't ask me to say
Yeah.
that, but yeah.
Okay, so now I think now my audio is closer to yours. Cool.
Okay, okay.
So F algebras. F algebras. So this thing is a little bit um, unexpected. Let's use that word. So it picks off from what we were talking before, which is um a definition of a monoid as a set, as a single object category, as an object of a monoidal category. So let's try to reinterpret the things that we just gathered. So we're gonna say that if you have these two things, you are a potential monoid, right? So this is what me, and I already forgot the name of this one,
Eta.
and eta. These are potential monoids. They are not monoids because we still have to verify the associativity in unit loss. We can
Yep.
use that mathematical algebraic notation from I don't know which chapter back in the day, and we can rewrite these things as this thing with the exponential and all that stuff because this is a function, and as we saw before, the parameter here becomes the exponent, and the result becomes the base.
Can I just say that's kind of wild having a number to the power of its own square?
Well, that's kind of wild. That's fair. So then we make the Cartesian product out of these two numbers, and then you use high school algebra to rewrite it like this. And if you go back and undo the process of using the notation, this represents this function. So now we combine the two requirements into a single requirement, which is this thing. Well,
Yep.
requirement to be potential, of course. Uh, then we can go further, right? What about a group? A group is the same thing plus a function that allows us to do inverse. So we established these will be the first three rules. Then you do this process, and that leads us to this thing
Yep.
for potential groups. And then we can also do the same for a ring, and then the thing can go crazy. Basically, the thing can go crazy. Uh, so first of all, we can replace sets with objects and functions with morphisms. We can replace n-ary operators as morphisms from n-ary products. We can this. It means that we need a category that supports finite products. The formulary operators require the existence of a terminal object. Um, Unary operators. Unary operators. So we need a Cartesian category. In order to combine these operators, we need the exponentials. So that's a Cartesian closed category. So like we are trying to establish if we go on and on and on and on, what would be the categorical requirements in order to pull this off.
Yep.
And finally, we need the coproduct to complete our algebraic shenanigans. To me, this is not 100% obvious because, well, we read a bunch of these things across the book. In terms of intuition, I guess it makes sense, but I would have to sit down and reread a bunch of stuff in order to 100% absorb this mapping. But I'm okay with it for now. Uh,
It's very okay.
it's very okay. Cool. So, uh, alternatively, we can forget about the way we derive our formulas. Like we can forget about the process itself, and just focus on the final product. The sum of products on the left-hand side of our morphism is defined as an endo functor. The question is why? Why does this define an endo functor?
Because, well, this is a very simple algebraic data type with a single type variable. So
Yeah, but I also think it's an endo functor, so it must go from it to itself, I guess.
it goes from its source category to itself. Yes, it needs to coexist in the same category as the base m that you picked for it, basically.
Yes. So then we're gonna call this functor f, right? And then we're gonna basically, okay. So what that means is that we all of the m stuff and operations we are kind of shrinking it down, like condensing it down to a single thing. And then the would be the type variable that would be how can you say that? Uh, oh, okay.
Or
Actually, I got it. The A is M, and the structure of these things is F.
yes,
Okay, that's the better way to explain it. The object is often called a carrier, an underlying object. In the context of the programming, the carrier type. The morphism is often called the evaluation function or the structure map. Um, so think of a functor f as forming expressions and the morphism is evaluating them. So this is crazy, right? So let's put this in other words because I think this doesn't do justice if you don't think if like it doesn't make it obvious what the heck it's happening here.
it's a
We
connection
are
to metaprogramming.
Yeah, this is an evaluator function. Like let that sink in for a moment. You know, like I don't Marinho knows, I know, but maybe I don't know. Some people are watching this. Think of Lisp's eval. That's what we are talking about.
Except it's actually typed.
Yeah. So it's kind of crazy. It's kind of insane because we are quite literally using category theory to not to explain but to elaborate to establish what could be any sort of arbitrary expression, which can be nested and all that stuff, as we are about to see.
Yep.
So this is very interesting. So here's the type, which is just the evaluator, and then we can define our previous examples in this mentality. So this is the monoid, right? So the mom f, it grabs the thing, and then it has the empty and the append with the two a's, and this represents this expression. Then you do the same with rings, and this represents this other expression, which are all connected. Remember, it all starts from the beginning with the separate requirements.
Yep.
Then uh, we can choose integer as the carrier, just as an example, and then we can define the evaluator of the ring. And notice something very important. The evaluator is not a recursive function. The evaluator is not a recursive function. That's really, really important.
It is.
And the reason is because, well, in simpler terms, the recursive process is going to be done by another guy.
Yeah.
The recursive process is going to
Foreshadowing.
be done by another guy. Which, by the way, is the entire point of my masters. It was to understand how can you make recursion with another guy. So that's
Dun
interesting.
dun dun.
Uh, okay. And then you can do the same. This is just with an integer example. You can do the same with matrices and polynomials and so on. So now let's go to that topic actually. So one way to generate arbitrary expression tree is to replace the variable a inside the function definition with recursion. What does that mean? In this data type, there is no a that is coming in and filling the blanks. We actually are calling ourselves. If you ever did any sort of very simple interpreter, everyone knows what this is about. Nothing too crazy.
Nothing new under the sun.
We can replace the original ring evaluator with its recursive version. Yeah, so this is that for, previous version doesn't have recursion. This one does, right? Because if you have an addition, like here, you don't have actually have the integers. You actually have you can have nested stuff, and then you
Yep.
need to have the leaves are actually the numbers themselves, and it's still not very practical. Uh, since we are
We are
forced to
first
represent all integer as sums of ones.
unary for the win.
But how do you describe expression trees using the language of F algebras? We have to somehow formalize the process of replacing the free type variable in the definition of our functor recursively, with the result of the replacement. So here's an example. So what are we doing? We are grabbing the original. So this is a little bit unfortunate, right? But this ring F, as far as my understanding goes, it is this ring F.
Yes.
And this ring F is not the same as this one. And the reason is because Haskell allows you to have two separate names. Well, the same name for two separate things. It,
Actually, the new name is on the left of the equal sign. It's ring F1 instead of ring F.
oh no, so this one actually is the same as this one in this case then.
It is, yeah.
Okay, so my bad, I got it wrong. So this thing is the same as we saw up there, and then we are nesting it one, that's why the number, and we are receiving the type variable. So we're filling the holes in the definition of ring F with the depth 0 trees generated by ring FA. And then we can continue this process, right? We can continue this process. And then again, why are we doing this? Why are we doing this?
Can I just say that the fact that the number on the name doesn't match the number of applications of ring F bothers me? Like it's off by one?
But the number is actually counting the number of set of parentheses.
Is it? Aren't you forgetting that there's a set of parentheses around the entire thing implicitly?
Implicitly, I can't see them. It's fine. Uh, and then of course, instead of doing this, you can actually use the previous one and so on and so forth. So this is actually, and the reason that we are doing this, I actually didn't say, is because we are trying to achieve this process. We're trying to achieve this sort of process without having to call the evaluator inside of the thing recursively, and not being forced to represent all integers as sums of ones.
Yep.
Uh, yeah, so that's why we're doing this. So conceptually, after repeating this process infinitely many times, we end up with the expression. So this process here, if you do it enough times, the end result will be the same as doing this thing, which doesn't have a type variable available.
It's being
Um,
filled up by itself.
the starting point of our journey doesn't matter. We always end up in the same place. This is a interesting. This is a very important thing to remember. This is not always true for an arbitrary and a functor in arbitrary category, but in the category set, things are nice. Of course, we need to explore this further. So applying an end of functor infinitely many times produces a fixed point. And this is the fixed point, which by the way, this is not the same version of the fixed point function in Haskell. This is the data type, as you can see down here, right? And this is
Yep.
the one that explains the confusion that I was trying to explain up there. This fix is not the same as this one. And then he even changes in the arguably saying that it's more readable if the constructor's name is different than the name of the type. So then we change this to fix in. So what does this does? This is a combinator called the fixed point combinator that is capable of executing recursion of an arbitrary function.
Although this one is defined on the type level, not the term level, so
Yes,
slightly different, but same concept.
yes. So this is interesting because a lot of the times when we are doing recursion or in our programs, we actually we we have conflated recursion with self-reference. We are usually led to believe that these two things are the same. And then this guy here is coming to us and saying, I don't think so. I can actually provide you the recursive process instead of you using self-reference. So that's interesting to think about. And then, as Manu said, in the type level, and then this is the type signature of that. And this guy has an inverse, which is unfix, that grabs the fix f. Well, in this particular case, it's a little bit unfortunate because he's not using in here. I don't know why, but this is just peeling off one layer of the process. Peeling off one layer of the process.
And by the way, unfix, awesome name. I'm going to start using it instead of breaking.
Okay, 1 second. Okay, I am back. Okay, I'm back.
Welcome back. So yeah, let's not break stuff anymore. Let's just unfix it.
Let's just unfix it.
Hello, Edu.
Hello. Okay, so now
Hello,
we. Hello, Edu.
just walking around.
Hi. Uh, so now that we
We are
discovered that we can do recursion in the type level without having to use, well, using this guy, what type of crazy things we can do with it? Um, well, here's the catch. We can actually pick our F algebras and use the fix in order to fix the problem that we just saw before. This thing. So now, uh, well, of course, in the beginning of the process, we need to define if algebras can form a category. And of course they do, because, well, a lot of things are categories. Um, but in this case, the objects of the categories are the algebras themselves. So an entire expression that can be nested and all that stuff, an entire, let's say, language, dialect, that is the object. And the morphisms uh, are ways that you can swap the algebras. Um, and of course, an algebra has a carrier object and a morphism that is the evaluator. So that's cool. So to complete the picture, our morphism must map one algebra, so it's a pair of the object and the evaluator, to another one. So imagine that you have the Haskell algebra and your morphism goes to Lisp algebra. Crazy. Crazy stuff. Uh, and then we're going to define a morphism M that maps the carriers. It goes from A to B in the original category. Not any morphism will do. We want it to be compatible with the two evaluators. So we need to take care that this M needs to respect F and G.
Yep.
Not any morphism will do. Yeah, I already read this. And here's a catch. This structure preserving morphism, this M, is an homomorphism because it preserves the structure. So, if M goes to A and B, what happens if you lift M? You are actually lifting the values inside their own algebras. So,
You were lifting the result,
yeah, the result.
the result of the evaluation, essentially.
Yeah, exactly. So now we can follow it with the G to get B. Equivalently, we can use F to go from FA to A and then follow it with M. So this diagram now is born. Uh, so we know that with M you can go from A to B. We know that from F of A you can go to F of B lifting M, and their evaluators do the vertical ones. Uh, and well, after all of this, you are asked to convince yourself that this indeed is form a category. The identity morphism from C works just fine, and composition of homomorphisms is an homomorphism. So that's good for now. But this is where I'm gonna ask questions to you, Marinho, because I don't know if I got this
Okay.
completely. This part.
Uh,
So let's go.
oh,
An initial object in the category of F algebras, if it exists, it's called an initial algebra. Let's call the carrier of this initial algebra I and its evaluator J. It turns out that J, the evaluator of the initial algebra, is an isomorphism. And that's important. I will ask questions about this later.
okay.
This result is known as the Lambec's theorem. The proof relies on the definition of the initial object, which requires that there will be a unique homomorphism M from it to any other algebra. Since M is a homomorphism, the following diagram must commute. So here's the catch. Uh, Essentially, we rename this thing, as far as I can tell. This. We
Yeah,
renamed
we
B with A and A with I, and M
yeah
and F with J, and G with
yeah
F.
yeah we just did a plain old
Alpha conversion.
variable replacement. Yeah.
Okay. Now let's construct an algebra whose carrier is Fi. So like we know we did the carrier as I, and now we want the carrier to be Fi. The evaluator of such algebra must be a morphism from that unpeels one F, basically. You
Yep.
can easily construct such an evaluator simply by lifting J. That makes total sense. Um, because Ij is the initial algebra, there must be a unique homomorphism M from it to this. And this is where my first question is. Why there must be unique?
Because if there wasn't, or if there was but it was not unique, then it wouldn't in fact be the initial algebra. Like that's part of what it means to be an
Initial.
initial. Yeah, that
Okay, so he should have said this here then. That the our homomorphism should be unique. Okay, cool. So the
it
following
does.
diagram must
It
commute. This is also a
it
bunch
does
of
say that.
renaming stuff, essentially. Do you agree?
Yep.
Just changing A to be f of I and changing F to be f of J. Everything else is the
Yep.
same.
Just variable
And then
replacement.
we also have this trivially commuting diagram. And this is a little bit um, weird because you're grabbing this thing and then you eval it, then you get rid of one F. If you pick the J on this, you go to I, and this is the same, right? This is the same thing. Like we are we are just reflecting this thing up here. Oh, you can see my mouse, right?
No, I cannot.
Thanks, Wayland. Which could be interpreted as showing that J is an homomorphism of algebras, mapping this thing to this thing. And then we glue the two diagrams together, and we form this other thing. So far so good. And then we go to the conclusion that the diagram may be interpreted as showing that J after M, so the
Yep.
bottom, um is a homomorphism. And the reason is because we're going from I to I. So that's the structure preserving. Um, Moreover, because this thing is initial, there can only be one homomorphism from it to itself. Yeah, it's what Marinho said before, and that's the identity amorphism ID on I, which is the homomorphism of algebras. Therefore, we also have that J after M.
Is the
J after
identity.
M is this identity. Using this fact and the commuting property of the left diagram, we can prove that M after J is the identity of f of I. Because if you see on the left side of the diagram, you go from f of I to using j to I, and then using m you go back to f of I. So this is also an identity, but in this time f of I.
Yep.
This shows that m is the inverse of j. That m is the inverse of j. And therefore j is an isomorphism between f of I and I. So because we know that this goes to identity and this also goes to identity, j and m are reverse to each other, inverse to each other, and therefore j is an isomorphism between f of I and
Yep.
I. It is an isomorphism because of these identities, right?
Yes, because these identities imply that in some sense M is the reverse of J.
Yeah, but
Like,
when we are talking about isomorphism, we need to use to define the other the oh we already did. It's j and m. Cool. But I'm just saying that I is a fixed point of f, right? So this is essentially saying that I is a fixed point of this thing, and that's
yeah.
basically the proof side of the hand waving argument. But then we can go back to Haskell and say we recognize I as our fix of f, j as our constructor fix, and its inverse is unfixed. The isomorphism in the theorem tells us that in order to get the initial algebra, we take the functor f and replace its argument a with fix of f. So that's going to matter later. We're going to see some examples. So here's an example with natural numbers. So we know that these will be the rules of this monoid. Then we apply the same process that we saw in the beginning. We get this thing. And then
It's
we
not
can
even a
translate this
it's
thing
not
to this thing.
well, it's not even a monoid at this point. It's literally just
Yeah. It's just an F algebra, right?
yeah, it's just piano numbers
Yeah,
as an F algebra.
exactly. So then you can write it like this, right? And then the fixed point of this functor can be encoded in Haskell as this thing. So after you apply the fix to this, the A disappears, and then you get this.
By the way, if you go up, uh, oh, this is not quite like. Does this remind you of anything?
Piano numbers.
No, no, no. I mean, like this is like this is basically a maybe actually.
This is a maybe.
It's
Elaborate.
isomorph. It's isomorphic to a maybe actually because like
No, of
a
course
nest.
it is.
Yeah.
Of course it is. I can tell you that much. Okay, so now the fancy names. Catamorphisms and anamorphisms. So, kata first. And by the way, I think at some point, and I also recommend, I should say this in the recording, I think that after going out through all this, it's very helpful for someone to actually go to the repo and actually put these things down there and see it working, because it's kind of unbelievable that this thing is calculating Fibonacci. You will never see this in any normal programming course ever. As a way to do Fibonacci. Let's go.
Let's
Uh,
go.
we call the initial algebra fix f. Its evaluator is the constructor fix. Okay, so now we are back to the constructor fix instead of in. There is a unique morphism m from the initial algebra to any other algebra over the same functor. Let's pick an algebra whose carry is a and the evaluator is alg. So again, alg is the evaluator. It is the non-recursive version because you're going to use fix to do the recursion. Remember, recursion is done by another guy. And so that means that when you pick f of a and apply alg, you're going to go to a. If you have a f of a fix of f and you f map m, so we are going all like inside this f, going to the fix and applying m to it, and that puts us at a. And if you fix this thing, you're gonna basically remove, well, remove this f outside, so it does this, And as we know, if you M this, you go to A, as we saw in the FMAP example. So this is the commuting diagram. So notice what M is. It's an evaluator for the fixed point and an evaluator for the whole recursive expression tree. Let's find a general way to implement this thing. So, and another point of detail is that we know that this bridge here, f fix of f to fix of f, if you reverse the arrow, you're gonna use unfix instead. So then you go to this one,
Yep.
and if you have this one, now we can express m in terms of it. You already could before. You can just compose the fix with m and the FL map of m and algebra. But that second one is more convenient because now you can just do this equality down here. We know that applying m should be the same as doing alg after FL map of m after unfix. So let's now go over the interpretation of this thing. The recursion is bound to terminate for any finite tree created using the functor f. We can see that by noticing that FL map m operates underneath, because here's the thing, unfix will peel off the level that you currently are, and then that means that we are one level above, one level below, sorry. So it operates underneath the top layer of the functor f, and in other words, it works on the children of the original tree. The children are always one level shallower than the original tree. Um, Here's what
Yeah.
happens when we up go.
As long as there's no laziness involved, your tree will be finite and this terminates.
Well, yes. Here's what happens when we apply m to a tree constructed using fix of f. The action of unfix peels off the constructor, exposing the top level of the tree. We then apply m to the children of the top node. So we unfix to expose the top layer, and then the fmap is the one that does the below action, and then the m is actually what is doing the eval. Again, think of Lisp's eval. This produces results of type A. So after this stage, we went to the children and we transformed the stuff there to A. Finally, we combine these results by applying the non-recursive evaluator alg. The key point is that our evaluator is a simple non-recursive function. So after all of this, now we're going to see an example, which again, I encourage anyone, including myself, to pick this, throw into the repo, discover where the heck this guy lives, import that, put this in the repo, put this, write this, and then try to calculate Fibonacci of, I don't know, whatever. Um, so since we can do this for any algebra alg, it makes sense to define a higher order function that takes the algebra as a parameter and gives us the function we called m. This higher order function is called catamorphism. So we grab the evaluator, the non-recursive evaluator, which is this thing, and we are basically, this is the return, right? You give us the initial value of the recursion, basically, and this thing will do the trick of getting you an A.
Yep.
This is M, right? So it's just called kata, but it's M.
Well, it's actually a constructor for m given an alg.
Well, yes. Let's see an example of that. So we make again the natural numbers, the piano numbers, and then now we're gonna make our evaluator, the non-recursive evaluator called Fibonacci, that basically establishes what should we do at a particular stage of the process. And then you may ask yourself, Fibonacci uses recursion. I don't see that being done in here. This is because this is being done here,
Yeah.
which is kind of crazy, but just try it out, read the types, you're going to be okay. You can convince yourself that the catamorphism for this algebra, kata fib, calculates Fibonacci numbers. In general, an algebra for NAT F defines a recurrence relation, the value of the current element in terms of the previous element. A catamorphism then evaluates the nth element of that sequence. And now this is fun because now we're going to see that basically, least length that you would think of by yourself. Oh, I'm just going to do a fold and that's it. You can actually implement the thing as well using an F algebra, which is interesting.
Now
So
lists are a kind of algebra. You just need to find the initial algebra for a list, which is this one, right?
yes. So this is what we would start. But then again, after you fix it enough, you hammer it down long enough, you're gonna get into this thing. But now let's try to use the catamorphism trick again. So now this is our non-recursive evaluator. Non-recursive evaluator. Kata is the same. We just swap the evaluator algebra for the algebra. So if you do this thing, it calculates the length of the list. Um, and then notice a pattern here. Notice that the evaluator is a combination of a function that takes a list element and an accumulator and returns a new accumulator, which is basically this guy, and a starting value, this guy. Does that remind you of something? Oh yeah, this thing. Uh, and the two arguments of fold are exactly the two components of the algebra. So another example, we have now this other evaluator, and this is just summing up the elements of the list, right? So we fold R is just a convenient specialization of a catamorphism to list. Very cool. And of course, it begs the question: what happens if you pick these diagrams and you reverse the direction of the arrows? The answer to that one is that you're gonna get this thing, a coalgebra.
Not
Uh,
something that people tend to think about, but very handy actually.
so if an algebra is something that picks something that is something and reduces it down to something else, this one is one that picks something and generates it up, which is cool. Uh, we don't have now an initial thingy, is a terminal thingy. So the terminal object is this thing in that category is called the terminal coalgebra. For every other algebra, AF, there is a unique homomorphism M that makes the following diagram commute. Um, so this is the same as we saw before, right?
Yeah,
This
just
thing.
flip the arrows.
Um, yes, just flip the arrows. The terminal coalgebra is a fixed point of the functor in the sense that the morphism, this thing, is an isomorphism, like symmetric to what we saw before. A terminal coalgebra is usually interpreted in programming as a recipe for generating data structures or transition systems. Just like a catamorphism can be used to evaluate initial algebra, and an amorphism can be used to co-evaluate a terminal coalgebra. So I know it's spoilers, but if like think by yourself, if fold is an algebra specialization, it is expected that unfold it is an anamorphism specialization,
And it is actually.
and it is. So and then this is kind of cool because you can really see how symmetrical they are. Because in the catamorphism, what was the first thing that we do? We unfix it. In this one, the last thing that we do is to fix it. So that's cool. And
Is to
then
unbreak it.
uh, and then the example that it gives us is the stream f, right? So streams. We've seen streams before. I think when we were talking about representable functors or something.
Yeah.
And then and this it's the fixed points of this thing. So I think it's exactly the same one as we saw in the older chapter there. So a coalgebra for stream f is a function that takes the seed of type A and produces a pair consisting of an element and a next seed. So you go from one thing to the one thing plus the new one, and kind of like a state monon in a sense. You can easily
Yeah.
generate simple examples of coalgebras that produce infinite sequences. And now we're gonna. This one is crazy. Like this one could be like a challenge in a functional programming course or something. So we're gonna write primes using anarmorphism. Crazy. So the trick is to use an infinite list as the carrier. our starting seed will be the least this thing. And then what I'm going to be doing at each iteration of the process, we will the next state of it will be everyone removed, everyone that was before, but removing the multiples of a particular prime. So uh, we start with 2, then we go over with 3, and so on and so forth. This is the evaluator, again, non-recursive.
The co-evaluator, in
The
fact.
co-evaluator, sorry, the co-evaluator. And then primes is just this. Recurse using this as as the transformation process along the way. And this is the initial value of it. Go on. And then boom, it gives you the primes. Uh, and then a stream is an infinite list, so it should be possible to convert it to a Haskell list. So now we are basically doing a natural transformation, right? Because
Right.
we are going from one functor to another one. To do that, we can use the functor streamf to form an algebra, and we can run a catamorphism over it. For instance, this is a catamorphism that converts a string to a list. So wait a moment. Are you telling me then that I uh, a catamorphism is a natural transformation then?
A catamorphism is a natural transformation. I guess it would be a special case of one, yes.
Because we are going from this, which is a functor, and this, which is a different one, to this, which is another different one.
Uh, I guess if you interpret this as like fixed stream f, if you interpret that as just being stream e, a like fixed stream f of e
Yes,
being
yes,
as
yes, yeah. You're talking
yeah,
about
then
reading this thing as this thing.
yeah, if you read it like that, then yeah, this is definitely a natural transformation because you are mapping a functor of a type variable to a different functor over the same type variable.
Yes, yes. Cool. Here, the same fixed point is simultaneously. Okay, this part is also the part that I'm gonna ask questions to you, Mani. The same fixed point is simultaneously an initial algebra and a terminal coalgebra. What does that mean?
The same fixed point is simultaneously an initial algebra and a terminal coalgebra. Well, basically, it you dropped.
Yeah.
Um, well, basically, like we saw that stream is well, it's a coalgebra, right? It's a final coalgebra,
Yeah.
and we saw that lists are an initial algebra. Well, there is an initial algebra for lists,
Yes.
and in Haskell they happen to actually coincide because Haskell lists can be infinite, which is basically like a stream essentially.
Ah, okay. So one of them starts at this point, and another one is going to that point. But one is going via coalgebra, and the other one is starting via algebra.
Yeah, like it's because like this wouldn't quite work in a nigger language because then streams and infinite streams and lists they wouldn't be the same, right? Because
Yes. Yes.
yeah, laziness in Haskell lets you do some crazy stuff with stuff that you would think of as finite but is actually potentially infinite.
It is not always like this in an arbitrary category. In general, another functor may have. Yeah, this is true for any type of thing. Not everything has a fixed point. And that's actually pretty important when you're using a fixed point because, and there are theorems, and I already forgot the name, but there is a book about it, like that establishes preconditions that in which the theorem tells you that there must be at least one fixed point. But is anyone remembering those conditions? Like that's I don't know about that one. Uh, so,
The
but
initial algebra is
it is
yeah,
something
I don't
fixed
remember
point
actually.
theorem Wikipedia. Yeah, this one. This one actually establishes preconditions, and I actually read this because of my master. So it's yeah, you need to establish that the operation that you're doing is actually a contraction mapping, which well, and then here's another thing. Fixed points, they are everywhere in many domains of engineering. So this one that I read was specifically about metric spaces, but um, this goes beyond any, like we are seeing it in Haskell category theory. Um, there's probably many other examples. There's in electrical engineering as well. But this one is the one that I know that it establishes preconditions in which you can be certain of the existence of at least. Actually, I think this one goes further. At least one. Uh, well, actually, not there. At least one. It is. There would be one, and it is unique, as far as I remember. Yeah, I admit it's a unique fixed point. So, is anyone remembering those preconditions to know if your recursive function will blow up or not? Up to the reader to decide. The initial algebra is so-called the least fixed point. And this is another nomenclature thingy. So if you search for least fixed point Wikipedia, there is a more mathematical definitions of what this means. And we also have in the algebra the greatest one. So these things, they are everywhere. I think it's important to mention that because these things are very cool. These things are very cool. There is a section about the notational semantics in the fixed
Uh,
point.
uh, Amazing.
Cool, cool. In Haskell, they both are defined by the same formula and they coincide. And then the anamorphism for lists is called unfold, as I said before, as a spoiler. So, and then you can use you actually need to provide a maybe. Well, a function that generates a maybe because it tells us when to stop the seed generation.
Yeah, because a list, unlike a stream, it may end,
Yeah.
right?
So, with that in mind, then there is something that I still have to figure out myself. This is the end of the chapter, which is lenses, right? I still haven't played with them. I read once about them, and I think I got what they are supposed to do, but I feel a little bit behind because I don't know how that's being done exactly. But apparently these things are in there. So a lens can be represented as a set of a pattern, a getter, and a setter. So for a little bit of a context for non-Haskell people, this is not what you are probably thinking if you say setter and getter. Many people, when they
Y-
heard setter and getter, they actually think of OOP, and then you think about Java and all that stuff. This is 100% not that. And what this is actually doing is the following. So as far as I can tell, the use case for lenses is because you have nesting on your data type. So let's suppose that you have a record, and then you create another one, and then you create another one, and then the final one uses all the ones above, and they are actually one inside the other, inside the other, inside the other. So the reason that, and that's inconvenient because you need to go under the layers and then update that one, and then update that field on that particular record, put that back into the owner of that, and then pick that and put that back in the owner of that one, and so on and so forth. So if you have a very nested structure of records or in types, you can actually use lenses to cross to do the unnesting and nesting back automatically.
Yeah, this is basically like a very. It's a crazy generalization of the functions like getting, associating, updating that you have in Clojure, for instance, right?
Yeah, exactly,
But
exactly. I and people may don't ask me how they work. I don't know, but there are posts about it. But anyway, so apparently these things that we are looking at, catamorphisms and anamorphisms, they participate in the construction of lenses. So a lens can be represented as these functions. Again, don't fool yourself. This is not Java stuff. And an A usually some product data type with a field of type S. The getter retrieves the value, So you pass the product type, and it will return you the value of a field of type S. And the setter replaces this field, right, and giving you the new value, which that's why we get another A. These
Yep.
two functions can be combined into one, and this is the result of combining, again, using a similar process to what we saw in the beginning. So you grab this, and then it's gonna give you the field in a function. That given a field of type S, it's gonna give you an A. You can rewrite this function further as this, and I think we also saw this before in previous chapters. I
Yeah,
don't
when we
remember
were
anymore
looking at
what
comonads.
context. Comonads, okay.
Comonads. Yeah.
And then where we have defined a functor. So basically this thing. Notice that this is not a simple algebraic functor constructed from sums of products. It involves an exponential
Yep.
because yeah, there is this function here. Uh, a lens is a coalgebra for this functor with the carrier type A. We've seen before that star S is also a comonad. It turns
Yep.
out that a well-behaved lens corresponds to a coalgebra that is compatible with the comonad structure. And we're going to talk more about this because the next chapter, which we're not going to be doing today, is algebras for monads, which is a cool title to say the least. And yeah, so the
Folds and
thing that
unfolds. It always seems to come back to folds and unfolds. And now we know why, right?
yeah, so I'm just taking a look on the comonads again because again, it's very hard for me to remember every single definition of this thing.
The intuition for comonad is you have a context, you have a focus inside of that
Now
context,
I
and
remember
you are
this.
yeah,
You have a focus. We'll continue.
and you are manipulating the focused portion of the comonad.
Hmm. Yeah. Yeah, I kind of now that I saw the class definition, it kind of makes sense.
which which sounds very similar to what lenses are supposed to do, right? Because you have this big nested data structure, which is your context.
And you want to
You are focused
focus.
on a small part of that data structure, you see?
Yeah, and as far as I can tell, there is a difference between lenses and optics, but don't quote me on that. But I think they, at least in terms of Haskell, these are two separate packages. And I heard that lenses are, in some particular use cases, annoying, and people prefer optics. But now it makes a lot of sense. Comonads is about focusing on a particular part, and lenses is actually exactly about this in a nested structure. So it makes a perfect amount of sense. Cool. So, and then a question that I have. That I was talking to Marinho in the server before about this. What, like, am I getting this right? Can we just go insane and make like a Haskell algebra and in
Uh,
Haskell, and do the same with like some sort of Lisp algebra, and then these things allow us going back and forth?
the difficulty with that is in both Haskell and in most Lisps you can have user-defined types, right? So the
No, no, but forgot about that. Let's say that it's just built-ins.
okay,
Because to
well you
do
could.
user-defined stuff, then I'm thinking about crazy stuff that's complicated. Let's just focus on built-ins.
Yeah, you definitely could. You could define a data type of Haskell types, like Haskell terms. You could define another data type for your Lisp terms. You could define the two evaluators, and um, or actually, you can define an evaluator that takes one and goes to the other, or vice versa.
But now I'm confused. That's not an
Which
indoor
is
functor anymore.
it is if those two data types are in the same, they happen to be in the same category. Like they don't like you were representing a Lisp expression in Haskell to do this, or you are
Yes.
representing a Haskell expression in Lisp if you're going the other way, right?
Also yes. But I think we're gonna have to make a data type to combine the two things again. So like data languages, and then we have Haskell and then Lisp, and then if we make the evaluator
Yeah,
of
if
the
you make an
languages,
evaluator, yeah, if you make an evaluator from one to the other, that's essentially a compiler.
well, yes, but I'm trying to, because as far as I can tell, in order to go from one to the other, we need a data type that puts them as two available options. Like you make your Haskell
Uh,
stuff, you make your Lisp stuff, then these data types for both of them,
no,
we need to,
actually
I
the
think we need to
evalu
combine them.
yeah, no, the evaluator, the way you combine them is by using the type parameter in your algebra definition, right? Because the evaluator, like the target language of your compiler would be the carrier type in your algebra in this case.
I don't get it. So let me pick an example. Here, let's pick the ring first. So I'm imagining making Haskell F in here, and then A, and then Haskell stuff.
Yeah,
Okay. Then we imagine this being the Lisp one. So then we put Lisp F A, and then the Lisp stuff.
yeah.
This is an endofunctor, and this is a separate endofunctor. And as far as I can tell, this thing that we saw about our F algebras, they are only about endofunctors.
Yes, and you could define an algebra that goes, for instance, if you want to compile Haskell into Lisp, okay?
Yeah, but
You
then
could define,
stop there. Do you agree you would have to make another data to do that, to combine those two things?
you don't actually.
That's the part that I'm missing then.
You can make algebra Haskell F fix Lisp F.
Wait. So data Haskell F equals
Algebra, no, no,
fix
no, no, not data, algebra, algebra. You see that, yeah, the
this one.
algebra type, yeah, that one.
Wait, repeat. So it's type algebra A,
Yeah,
type
no,
Haskell algebra.
no, 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 no. It's literally just algebra. F is Haskell F, and A is fix Lisp F.
Wait a moment. You're saying that F is going to be Haskell's and A is going to be Lisp's.
Yes, and yeah, if you're doing a compiler from Haskell to Lisp, F is Haskell F, and A is fix of um, Lisp F.
Wait a moment. Because now I think I'm more confused than before. Because F is the one that allows us to express structure using values of the carrier type
Yes, and you are taking the structure.
of Haskell stuff. But
Yeah,
the
you're
nodes
taking this.
themselves, they have Lisp stuff.
Yeah, because basically you're starting like this is the actual algebra, right? The initial algebra that you are starting from would be fix of Haskell F, actually, right?
Hmm.
Uh, and if you want to have, okay, I have, if you want to transform that into a fix of Lisp F, you need an algorithm that takes Haskell F of fix Lisp F and returns a fix Lisp F. Uh, and you're going to pass that algorithm
Evaluator.
to your catamorphism. The algorithm is the evaluator, actually.
I can't say that I 100% have the vision because to me it's a little bit unnatural that the structure is Haskell's but the nodes have Lisp stuff.
That's because the Haskell F with Lisp inside of it is a structure denoting, okay, I'm in the final step of the compilation process. I have this top level Haskell term. All of the inner nodes have already been translated. How do I translate the final
Ah,
layer?
okay, that helped me a lot. So you're actually at a final phase process in which everything else that is already nested is already being translated to Lisp, and you are basically just doing one layer operation, I guess.
Yes, and then you take that one layer operation, your eval. In this case, it would be more proper to call it a compile, but whatever.
Compile. Yeah.
And you pass it to your kata operator, and that's your full compiler defined in terms of a single layer, basically.
Yeah, but that's kind of boring though. I was kind of thinking, how could we use this to have a complete Haskell program in having the final like having a real compiler from not only the final layer. Is that
No, but
possible?
that's no, it is. If you take kata and you partially apply it to your final layer, you get your complete compiler because it takes a fix of Haskell F to to a fix of Lisp
No, no,
F.
no. But in your example, we already have Lisp stuff in the layer above the top, no, below the top. I'm,
Well,
I'm
if you
you have a you have a I'm talking about having only Haskell in the beginning. You have a
yes,
gigantic tree of only Haskell stuff.
yes, that's the fix of Haskell F,
That's the fix of Haskell
which
S. Okay, but how how I'm gonna convert the leaves first to Lisp?
that's what the catamorphism is for. It will basically drill
Ah,
down, you see?
so they start kind of empty, and then we go like populating with Lisps instead of Haskells, I guess.
Yeah, basically. Because if you
Ah.
take the catamorphism and you partially apply it to the step in terms of Haskell F of the fixed
Mhm.
Lisp
Mhm.
F, that's the catamorphism will drill that down to the lowest leaf and start building up the Lisp tree from there, essentially.
Yeah. No. That I think you explained it pretty good. It is indeed Haskell stuff on the F and Lisp stuff on the A. But the A starts kind of empty in a sense.
Yeah, and you can of course go the other way around. I just chose Haskell to Lisp because it felt appropriate in this case.
Mhm. That's crazy. This is crazy.
That's
Uh,
compilers for you.
yeah, no, but this is a completely different way of thinking about it. We are not thinking in terms of. Uh, no, we are kind of thinking in terms of representation, but not in the sense that anybody does. We don't have a bunch of text, then a bunch of tokens, then an
No, no,
EST,
no, no. Yeah,
then.
no. This is like, okay, here's your Haskell AST,
Jeez.
here's your Lisp AST, here's a mapping between them. It is an algebra.
Yeah, and then you literally. Okay, that's a little bit misleading because you're gonna have a little bit of trouble because this guy you're gonna have to write yourself.
Yeah, that's the hard part,
That's
actually.
the hard part. That's fair. But, well, in that particular case, then, it's not that different in terms of work. It's the, like, you're going to have to parse the stuff. You're going to, well, Lexer or use a Lexer or just a parsing process, doesn't matter. You're going to have to end up constructing the Haskell F and the Lisp F anyway. You're going to start with the Haskell F in this case. Then you're going to have to write this operation, which is basically what you would do anyway in a normal normie way of doing a compiler. Um, but the difference is that you would call the recurse use you would do the recursion using self-reference like this guy. Instead, you are opting to not do that and just using the kata as a way to do it for you. So the gains are not that insane in terms of usability, but the fact that you can fit such an important process of programming using this thing is cool. Definitely cool.
Compilers, man, they are important.
They're what?
They are important,
They
of
are,
course.
yeah, no, and they seem to be everywhere. This we just saw. This is a category theory book, and it's talking about evolve and all that stuff. Anyway, I'm gonna stop the recording now.
Bye, future people.